This is the mechanical lubricator, and what we do is we fill this up full of steam cylinder oil right to full. It keeps using this all the time as you're going. This keeps going back and forth, and it keeps using the oil level down. You have to keep this full, or bad things will happen to your steam cylinders and your air pumps. The valve oil is mixed with the steam as it's going into the cylinders, and that lubricates everything in the cylinder. This rod is actuated off of the rod that comes from the wheel, and it just moves this back and forth. And what it does, it keeps cranking this around a little bit at a time, and it keeps pumping oil to your steam cylinders and to your air pump. This just kind of primes the oiling system so you have plenty to roll with to start with. And there's approximately 70 some oiling places on the whole engine, about 35 per side. We're first going to start lubricating. This is the bottom arm of the Johnson bar. This is the brake arm. These are your suspension joints. Some of these oiling places are kind of hidden. You can't see them yet, you just know where they're at. Right now we're oiling the Baker valve gear. What we're using for general lubrication is journal oil. Use the same thing in the main journal boxes on the engine and also on the train. These are the oil caps, and before you run on the roll you crack these about a half a turn, and it just drips oil down to lubricate your slides when it's going back and forth. This gives a little bit of pre-lubrication before you start out in here. What we have here is we just have pipes out of the top of the pony truck journal boxes. We just fill that with oil. That way your front pony trucks or the wheels get lubrication. We're now going to lubricate the main drive journal bearings to the drivers. And these are just open holes in the top of these boxes. The whole weight of the engine rides on your driver, other than just the pony truck. And we're talking 75 tons plus the weight of the water, over 80 tons riding on these bearings. We're going to pack the rod pins with a pin dope, which is a real heavy grease. And how that works is as you're rolling along, the friction in the grease itself melts it and keeps adding grease to your brass and your rods. What you have is a steel rod coming out from your main drive wheel, which is steel, and then you have two halves of the rod brass on each end. And as these wear down, these can be adjusted, move closer to take up the slack. But you have to keep them doped all the time. You don't dare let them run dry and things heat up, and then the brass will gall. We're now going to push pin dope down into the rod pin in order to lubricate the brass bearings in these rods. We run the grease caps down until we see grease coming out. That we know if they are lubricated. And if they feel hot to the hand where you can't touch them, you know they're getting hot. That same goes for your journal bearings. If they get hot, you can feel it on the side of the wheel if they're heating up. Because that one will be hotter than this one. And if it feels hot to the hand where you can't touch it, you know you didn't either get enough lubrication or you have a main problem. I leave the grease caps up fairly high so we can lubricate these between runs. We run short on time between runs. All we have to do is crank these down. We don't have to take the grease cap all the way out and put new pin dope in. We got enough in there to last the whole day.
Well, it was during the war and they were short of help down here, so they come and asked me if I'd want to go railroading, so I thought I'd come and give it a try. I started railroading on July the 13th of 1942, and I became a fireman about 13 days later, and I continued firing steam engine until about 1946. In 1946, I was promoted to engineer on the steam engines. When I started as engineer, it was much different than it is nowadays with the modernization of equipment. When I started out to be an engineer, I had to put so many hours as fireman and so many hours breaking in as an engineer. And you run it to a time where they thought you were qualified. And a lot of the time you was learning how to qualify as an engineer. You had to study books called The Science of Locomotive Engines. You had to study those books, and you had to study train operating rules, the book of rules of the railroad. And when they thought you were qualified for an engineer, you had to go to the master mechanic office and take a written test on the workings of a locomotive. And when you finished that test, you had to go to the superintendent's office and take a written and oral test of the operations of the whole railroad. And then if you passed the test, you became an engineer, and they give you a seniority date on the day you passed the test. Well, I think working around the railroad, I think it is just something that grows on you. The more you get into it, the better you like it. And you just become accustomed to it, and you stick with it.
I'm a boilermaker by trade, and they had come up with a mechanical problem on the engine, a slight boiler leak. And rather than contact someone from Sacramento or from Carson City, I was contacted to see if I could help. And luckily I was able to help with the problem, and I got help. although we do go with the book learning, we rely on people like Joe and the others in the community that did this for a living. And they learned it the hard way, and they know the easy ways around things. The book tells you a straight, staid method, and we try to learn it just the way it was taught to our predecessors. The experience of these old guys, we hope to be able to follow in their footsteps and hope to be able to do it wisely. And they've left us a great treasure, and I just hope we can maintain it for them.
Okay, we're going to start the train. We're going to back up, so I'll give a signal. 3 short blasts on the whistle signifies backup. And I'll move the reverse lever all the way back, release the brake, and pull the throttle out easy. I gotta watch out for signals back here. I'm gonna stop the engine when you're over the switch. Using the engine brakes very lightly. It's a hard baby to move because it doesn't have air on it. You got to move strictly by muscle. Now I release the engine brakes and the train brake. Pull out on the throttle, which will move the engine ahead. When you move it out lightly, you don't give it too much speed. Okay, I got to set this junction bar so it's not quite as much power. Go down a little, so I'll push in on the throttle. Just kind of let the engine coast until I need more power. Then I pull the throttle out of it. Fairly level ground here, so it doesn't take too much power to move the train. So keep the Johnson bar hooked up close to the center, and the throttle will get fairly cracked open. Now we're starting up a grade now, so I'll give it more steep. And as it requires more power, I'll move the Johnson bar down a notch at a time. Each time I move the Johnson bar 1 notch, I increase the power that the engine's putting out on the drivers. If you listen to the smokestack, you can tell when the power is increasing because the noise of the exhaust will increase a certain amount. Now hook Johnson bar 1 notch. So I'm going to move the Johnson bar down. A little more speed. We're heading up pretty good grade here, so it takes a little more power. Move the Johnson bar down. Increases the power. A little more throttle. All there is a combination to kind of work your throttle in accordance with your Johnson bar. I like this engine. It's a good engine. It's a smooth running engine. It doesn't give me any trouble. It's got a small boiler and a small firebox. It steams good and runs good. Very good engine.
That's the only thing you might encounter on this particular section of track. You'd have to watch for things on the track. People walking along the track, kids playing along the track, or anything that might interfere with the operation of the engine going up the track. Now this particular section of the track kind of flattens out, so consequently we don't need no power. So we can cut down on our throttle a little bit. So where it cuts the amount of steam that you're using, and at the same token it keeps your engine rolling to the speed that is required to handle the train. But you have to watch your water glass at all times, make sure that the water glass has plenty of water on it. At the same time you have to be alert and watch your track, not only going forward, but you have to look back and make sure that everything is all right in the back of the train. Okay, we're going to make a stop here. We have a very light train, so all we take to stop it is just the engine brakes. If you apply the engine brakes very lightly, this length of the train, it doesn't take much brakes to stop it. We're going to make a brief stop here.
Okay, on this side. Monitoring both the fire by adding coal, making sure that the fire stays at a nice even level in order to supply satisfactory steam for the engineer. To turn on the injector, I first have to open the primer, and as I do, I check the primer pipe to make sure that it's spewing water instead of steam. When the water comes, I open the water and turn off the primer, and then I monitor my water level through my water glass. When I've determined that there's enough water level in the boiler, we also use that to help control the temperature of the boiler and the pressure. I then turn this handle off, and that shuts off the injector. Having achieved the temperature drop that I was after, I'll go ahead and shut the injector off, and then continue to monitor both my water level in my water glass and my pressure on the pressure gauge. Another function that the fireman serves, because of the size of the locomotive, he's an extra set of eyes and ears for the engineer on this side, since the engineer can't see both sides of the locomotive at the same time. We're entering a steep part of the hill, so we need a little bit more wire in order to pull the grade. With some sort of a pattern, I work the front corners, the side, the back, and then down through the center. On this point, I've also got the injector going to bring my water level up in my boiler. So I have to shovel a little bit harder to combat the cooling effect of the water that's going into the boiler. And that's known as firing against the gun, which is where the old term of being up against the gun came from firing against the cold water coming into the boiler. Woo!
Okay, we're starting downhill, so we'll start using automatic brake valves to control the train. First I'll make a reduction. That's drawn air out of the train line. After I make application of train brakes, I'll hold it right there. No air comes out of the train, no air goes back. To release the brakes, air has to go back in the train line, so I'll put the automatic brake valve in release position. As the train picks up momentum, I will have to draw more air out of the train line, which in turn sets up the brakes on the train. And I'll keep them set up until I reach the speed I want, and then I will release the brakes. If you're going downhill, it's just more or less a repetition of drawing the air off of your train to set the brakes on your train. And when you get the train at the speed you want it to maintain. Yeah, the engine brakes can't control the weight of a train. Use the automatic brake valve because it completely controls the brakes on your train. You cannot use the engine brakes. If you do use the engine brakes, you use them very lightly. Because your wheels on your engine, it's excessive use of the engine brakes will cause buildup of the heat on your wheels. So, to control your train brakes, you use strictly the automatic brake valve.
My water glass is right here. The engineer can see the water glass directly from his side of the cab and can monitor the water level. I can monitor it from my position simply by looking at this mirror and seeing the reflection and judging where our water level is. You never want your water level to drop below the lowest point of the crown sheet, which is shown here on the back center of the boiler by a steel plate with a line on it. Should it ever get to a point below the level of the crown sheet is then exposed to fire all from one side and can lead to failure because the fire will soften the metal, and with the pressure, which our boiler runs 175 pounds, it can lead to failure of the crown sheet and a resulting boiler explosion.
Fellers that I've worked with here they are good fellers, they're conscientious, and they catch on pretty fast, and I show them what to do and they pick it up. I don't have to tell them too many times. We did have one young lady we broke in. She was one of the first engineers, and I was surprised at how much a young lady like that could learn and how fast she could learn it. And I just hope that in the future they'll probably have another 2 or 3 engineers on this engine.
I'm breaking in as an engineer, and Joe asked me if I wanted to go ahead and run, and he took the firing. Well, for most of us, it takes great big shovelfuls of coal, and Joe, with 39 years of past experience, can do it with a little nugget here and a little nugget there. It's more of a knowing where to put it rather than how much you put in the boiler. These are the things we still have to refine. Maybe save a little bit on the expense down the line on our coal.
This locomotive was outshopped by the Baldwin Locomotive Works in Philadelphia, Pennsylvania in March of 1921. There was an order of, I believe, 14 or 15 of these built at that time. The engine went into service in April of 1921. It remained in service constantly until January of 1957. It was one of the last engines to operate in the San Francisco-San Jose commute service. From 1921, when it went into service, until in the late 20s, these were the premier passenger locomotives on the Southern Pacific, handling all of the great name trains. And this engine operated for a long while on the Overland Limited and trains like that between Sparks, Nevada and Ogden, Utah, which is 535 miles. At that time, it was the longest unassisted run by any locomotive in the United States. At that time, the Southern Pacific bought 10 mountain-type locomotives. Looked very similar to this, except they had one more driver. They had 8 drivers instead of 6. But they had a bigger cylinder and they were capable of doing much heavier work. These engines at that time were downgraded somewhat to handling the mail trains and a more secondary type of trains over the system. And then when World War II started, in the 40s, even when America started building up, these engines again went back to working very, very hard. All through the war, these engines were handling 12 and 14 Pullman cars full of military personnel at high speeds, and they were once again a real mainline locomotive. With the close of World War II, the Peninsula commute service here between San Francisco and San Jose was building up. Suburbia had started. People were living out of town, commuting, and the commute traffic had gotten up to, I believe, around 20,000 a day. And these engines once again were pulling 10, 11, and even 12-car commuter trains on the peninsula. As the bigger engines were released, the passenger traffic dwindled on the main line, the passenger trains were discontinued. Bigger engines became available for the commute service, and many of the lighter Pacific class locomotives, that's what this is called, the Pacific class, were junked in the early 50s, and these engines gradually slipped down to where they were working the lighter 2 or 3 car midday and late night locals, which is where this engine ended up.
I want to make sure the steam vent is open. I can see the steam coming out of it. So I know there's steam in the boiler. At the same time, I don't want steam going into the cylinder so the engine doesn't move. All right, I'm going to go up, I'm going to remove the stack cover, then I'm going to walk down the top and I'm going to turn on the turret valve to make sure I get steam from the boiler into my manifold, into the fireman's manifold. Now, before I go into the cab, I'm going to walk around the engine to see if there's any chains or blocks or anything of that sort under the wheels. Make sure there isn't anything under there that I don't know about before we move it. That looks pretty good.
Like the old fella says, the drop on the machinery is worth a whole can on the ground. But that's generally where it ends up. But lubrication is very important because oil is really very cheap compared to manufacturing new parts and the engine failing out on the road due to hot pins, driving boxes, etc. The driving wheels are all equipped with a grease cake, what we call a grease cake lubricator under there. And that is what the stars on the center of the wheels designate. Everybody thought Southern Pacific did that to pretty them up. Not true. It meant that the engine was equipped with grease pad lubricators. What it is a pad made of grease. It's held by a metal container. It's shaped to fit the bottom of the axle. There's springs underneath it which keep it pushed up against the bottom of the axle like this, so that it's leaking. This is what I told you about a can on the ground. Anyway, as the axle turns in here, this simply rubs on it and the axle is constantly picking up a small amount of grease. That's how they're lubricated. This is a trailing wheel. One axle, there's 47,000 pounds resting on these two wheels. And inside here is the bearing for this. This is the axle, and this is the bearing. This is what we call a flat back bearing. You can see it right around here is the white, what we call white metal or babbitt. And this axle rotates in this. Down in the bottom here is a pad that rubs on the bottom of the axle, and you can look through the little window here and you see that's full of oil. So that means there's proper lubrication in there. The valve motion here, which is all of this. These are all grease fittings here, and we use a kind of a graphited type of grease, which holds up. It's very, very good lubricant. We don't need the real heavy grease there because we do not have the pressure or the movement that we have on these bearings here. These bearings here are going a full circle. Most of these bearings here are simply rocking type of thing. There's not a heck of a lot of movement there, and that graphited type of grease holds up very well. Now, there's a lot of oil. Lots of things to oil on here. The cylinders and the valves, this is the valve up here, and this is the cylinder, 25 by 30. This has a 9-inch diameter valve in here, which is shaped like a spool. And I'll show you in a moment. This valve motion here moves that back and forth. At 75 miles an hour, this locomotive is making about 350 revolutions per minute, which means that this piston in here, this piston and this rod has to weigh at least 1,000 pounds. This thing is starting here, goes back here, and goes back here about 6 times per second, which would produce about 350 RPM on the engine, which means the valve has to admit steam here to push the piston back, then it has to exhaust it, then it has to admit steam here to push this piston back, then it has to exhaust. It has to do that 6 times a second. That probably doesn't sound too exciting to people that are into high tech, but when you stop to consider the weight involved, the rough service, and the volumes involved, it's really quite remarkable. This is a force feed, or a mechanical lubricator. This is a 6-feed lubricator, and the lines are here coming off the back of it. What we have up here are 4 lines. One of these goes to the valve, and one of them goes to the cylinder. Same on the other side. The other 2 lines, one here goes down to here and lubricates the bottom of the top guide here. This, you have to remember, is flying back and forth at a very high rate of speed, plus there is a lot of pressure on this. Now, oiling. Oiling, there's lots of oiling. Lots of oiling. For instance, the lower guide here, you see this stuff in here? We put some oil in here, you see. The waste in here holds the oil and lets it dribble out over a prolonged period of time. So you have one in the front and one in the back here. That oils your bottom guide. If you're going to oil around too, pay to put some on here like this. When you are oiling, you're looking. And you would be surprised. You'll find loose bolts, keys out of pins, all kinds of things like that. So that is another reason to be oiling. The railroad wanted you to get down and oil every time you stopped for water. And it was amazing. Guys would find defects that before they turned into an accident. Now, the rods, the main rod, the side rods, all that, we use a very heavy pin grease. It's about like a very, very stiff modeling clay. And it holds up very well under high pressure and heat.
Getting low on steam and we have to get this baby going. So I guess the first procedure is, first thing we do is we check the water. Get water out of the bottom one and to get steam out of the top one, which we have. That means that the gauge is properly adjusted, and the middle one should also get water. Yeah, right. Okay, I guess the next thing to do is we're going to have to open the damper, the back damper. That gives us air into the firebox. We're going to have to open the oil valve up here. Okay. We have a good supply of water in the tender, so we're all right there. All right, now we have to open the manifold to get steam to all of the valves and everything. Okay. And we want to blow out the atomizer, make sure we have no, get the water out of that. Crack the blower about a quarter turn, get some draft going. So we get a little draft through the firebox. Yeah, you feel it's starting to suck now. Get some oil on this waste so it'll burn for me. Got to get it in the center this time. All right. There it's taken. You can see it starting to flare up inside. When you open this firing valve, you do it 1 notch at a time. You keep your finger right next to it so that you can feel it when it opens up that 1 notch, because 1 notch affects the fire considerably. We'll close the door now. Okay. Looking pretty good. Just have to let her warm up now.
Oh, what do you say, Neil? What time is it? All right, you about right? That looks pretty good. Pretty good. All right. Okay. All right. How you doing, Ron?
Oh, pretty good.
How's she look?
It's coming together.
70 pounds, okay.
Yeah, take a check here. All right, looks good.
Pick up and give it a... You got it, Ron. 719 gallons, Neil. 719. And about a little over 3/4 tank of water.
Okay. Take a little look in here.
Yeah, better check it out.
See if anything's falling apart.
Look okay?
Yeah, good and dry, nice and dry.
All right, good. Give her a kick in the pants a little bit and see if we can get some steam up.
Okay. Well,
I started firing in 1951. I was just a young kid right out of high school. I went over to the Southern Pacific on the Coast Division here in June of '51. And then I went through a series of student firing trips, a lot of yard work. I think Neil and I were kind of figuring out about 600-700 hours of yard work before we even got out on the main line. But anyway, in those days, we wanted to make our, as they call it, we make our date, our first actual firing job by ourselves. That was our seniority date. So we tried to get that in as quick as possible so we would get as much seniority as we possibly could. And so it was like 8 on and 8 off. You know, we'd work a shift and we'd go home, sleep a while, and come right back and work another shift. Just got it in as quick as we could. And I made my date. I started around, I was graduated June the 6th, and I was probably in the SP hospital going through physicals and that sort of thing, and examinations and so forth, around the 10th of June, and I made my date October the 4th. So it was quite an extensive program, and this was with no time off, just like 8 on, 8 off, just working all the time. And what prompted me to go to the SP is I just was always in love with steam. I mean, as a kid, I just loved to watch these things go by, and it was always my dream to fire steam engines and be in the engine crew and eventually be an engineer. What we got here on the fireman's side of this road engine is, first of all, this is the manifold valve. It allows steam from the turret down this line here into my manifold, which is basically broken up into other various valves for controlling the fire. This gauge up here, this valve here is the water glass, or the upper valve to the water glass, which allows the water, or the steam part of the boiler, to come on down into the top of the water glass. This is the valve for the bottom. It allows it to come up, and this is also the drain valve. Now when we open this drain valve, the steam pressure in the boiler will blow the water out. You'll hear that, and then it should come back if everything is working normally. All right, now the water does come back in the gauge, so I know this gauge is operating pretty well. All right, now we get down to the actual firing of the engine. This, of course, is the firebox. This is the firebox door, and I'll give you a little picture of the fire. We'll open it, and we've got a little fire rolling in there right now. This is the peephole, and we cut it down a little bit just so I can see the color of the fire from where I'm sitting. Now, this is the firing valve. This is the firing pin, which is used to set your spot fire and actually control the movement of the valve so you don't put your fire up by shutting the oil off too quickly. This is the quadrant here. You can see a lot of little teeth on here. And we actually fire the engine by moving the firing valve a notch at a time, basically. They call that walking the valve. We've got 2 brass valves here. One's a water valve and one's a steam valve. This is our injector. This is the second way we get water into the boiler. This is the way we'll use while we're not working steam. Feed water pump is basically the same way, except it's a heating pump. And you work this when you're working steam in the engine. So in other words, if the engineer's got the throttle open and we're going down the main line and we have the blower off because we have enough draft going through the firebox by the simple exhausting of the locomotive, then we can crack the water pump and we can operate off of here. This is by far much more efficient. It heats the water much better, gets a little hotter than the injector, and you don't lose any water. Everything is kind of a closed circuit. Pump it right into the boiler. As long as this gauge is moving back and forth, you know your pump is operating. Okay. This gauge is the steam heat, and of course the old cars, we were equipped here with this boiler to steam heat the coaches. And basically, we would give 10 pounds of steam heat per each coach with a minimum of 50 pounds. This engine fires and works on 210 pounds of steam pressure. This is my gauge here. The engineer also has one on his side, as well as a water glass. Now, the only other valve that I've missed here, I don't know if you can see it or not, but back here is it's a blowdown valve. And what it does, it blows. When we start to move the locomotive early in the morning, we get a lot of sediment that's been built up in the boiler, and it settles to the bottom of the mud ring. It's a lower part. This valve is located in the lower part of the boiler, so all the sediment sits there. And then we give this boiler a little blow, and I'll pull this valve back, and that'll blow off the sediment and the impurities in the boiler. It tends to keep it clean.
I started out in 1944 in the roundhouse at San Jose, and then went out on the road firing and was promoted to locomotive engineer in 1954. And I had the good fortune to fire and run this locomotive when it was in daily service. Now, John has told you what was required becoming a fireman. A locomotive engineer on steam. Now this is not true today, but during John's time and my time on steam, it was required that you had 3 years of firing experience before you were even eligible for promotion to locomotive engineer, which required a physical examination. Then we took 2 written examinations. One mechanical examination, which was about, if I remember right, about 390 questions and answers. It generally took 2 days to do it. About a week later, you went back and did the Book of Rules examination, which I believe was around 600 questions. And depending on how smart you were and how fast you could write, it took 1 long day or 2 more days to do that. After you were promoted, you had to have 680 days on the road before you were qualified for passenger train service. And after that, well, that was it. But it's not something that happened in a year or 2 or 3. I fired 10 years and before I was promoted. It wasn't that I couldn't have been promoted earlier. It was that I wasn't needed as an engineer. It's a seniority deal, and it depended on how badly they needed men. There's a lot of things over here to look at, and it looks very complex. Actually, it's not really that complex. The main thing with the steam engine is maintaining a safe water level in the boiler at all times. This engine is equipped with 5 fusible plugs. We call them soft plugs. And if the water gets too low, before any of the metal sheets are burned, the crown sheet, which is the top sheet in the boiler, and it basically runs right below this row of plugs here. These plugs can be removed to get in and wash the crown sheet when we do boiler washing. Actually, when the water is at the bottom of your water glass here, or over here, you still have about 3.5 to 4 inches of water on top of the crown sheet. That is a safety factor, and it's required. If the water gets too low, gets down to about only 1 inch of water on top of the crown sheet, these fusible plugs are held in by a lead solder type of thing, which melts at a predetermined temperature. The plugs will then function, which will blow out the fusible plug, which is about 3/4 of an inch in diameter, and the steam and water in the boiler go down into the firebox and extinguish the fire. This prevents overheating of the crown sheet, which could result in a boiler explosion. Actually, everyone seems to be very afraid about boiler explosions. Actually, you consider the number of boiler explosions they ever had, really considering the number of engines and the amount of hours of service, they're really very, very safe. We blow these glasses down quite frequently because they have had experiences where boiler scale, foreign material and one thing or another, getting in here and plugging up the passageway in here, and the glass then gives a false reading. So we periodically boil them down, the water goes completely out, and then you observe that it comes back up again at approximately the same level that it was at again. Back up to the manifold, or certain things here concern me. This valve here turns on the lubricator, the steam. This is a hydrostatic lubricator made by the Nathan Manufacturing Company. It is a 3-feed lubricator. We're only using 2 of them. This one, this handle lubricates the water pump, and this one here, the air compressor. This works on the theory that oil floats on top of water. What happens, the water comes down here, this is full of oil. Right now it's full. We have what we call a bullseye here. You can look through here, it's glass here and glass here. In the middle is the oil, this is all full of oil. So to check and see if the lubricator is full, you look through the glass here. If you can't see through the glass, it means it's full, because you can't see through the oil. Again, we have a bullseye glass here, and I can see all the way through here. All there is in there is water. Now, before, about 15 minutes before starting the water pump or the air compressor, you turn this, and you regulate it, you look through here, and you'll see little drops of oil going up. They go up and out through these lubrication lines here to wherever they're going, the air compressor or the water pump. This holds one of these canfuls here of oil. This can here is full of what we call valve oil, or steam cylinder oil is probably a better name for it. It's a very heavy oil, and it holds up very well under steam and water. Again, I have a steam gauge here which is calibrated with John's. They both read the same, so I can see how he's doing. This is the air gauge. There is a pipe all the way back through the train called a brake pipe, train line, whatever you want to call it, and that supplies air to the cars and the locomotive for the operation of the air brake. This, of course, is a throttle, and it has a lot of notches here, as you can see on it, and of course, the farther out you bring the throttle, why, the more steam you're admitting into the valves and the cylinders. These are the 2 brake valves. The little one here is an Westinghouse S6 valve, and it has 5 positions over here. This is where it's normally carried. This is with the brakes released. This applies the brake on the engine and tender only. And this is a release position here, and this is where it is normally carried when we're out on the road. You come up over the hump here, that's what we call lap. You bring it here, it's slow application. It builds the brake cylinder pressure up very slowly. If you're in a hurry, you come over here against the spring, and that's called quick application over there, and it applies the brake more rapidly. This is a lap position. In other words, if you want to bring it over here and put 20 pounds in, and then you put it there, and then it just holds it at 20 pounds. It does not add or subtract from it. Okay, this is tied in with this. This is the automatic brake valve. This applies the brakes on the cars and the locomotive, and all the way over is emergency, commonly called big hole on the railroad, simply because it lines the largest port up in the brake valve with the atmosphere and applies the brake at a very rapid rate. This is a sander valve, and this out in front of the driving wheels, we have some pipes come down from the sand dome, which is up on top of the boiler. When we open this, air goes out to the sand trap and blows sand down the pipes in front of the driving wheels, and it sprinkles it on the rail right ahead of the drivers. Sand increases the adhesion between the wheel and the rail, and is very helpful in starting heavy trains or on slippery rail. It's also beneficial in braking. Excessive use of the sand is is not recommended. Some people may remember years ago the little wire running down the middle of all of the cars, and the conductor would reach up there to get a hold of that wire and pull it. Well, what happened? This little whistle would sound down here. For instance, if you were standing still and the little whistle blew 3 times, it meant they wanted to back up. If you were running and the little whistle blew 3 times, it meant stop at the next station. But we had whistle signals for just about everything. If we didn't have a whistle signal, we had hand signals. It was really a wonderful way to work. It's almost a lost art today. You see very few hand signals anymore. You see them going around with a light locomotive, and one guy is talking to the engineer over the radio, and he's 40 feet away. But it was really a very nice way to work. It was really an art to watch some of the people on the ground, switchmen, brakemen, conductors. We could work all day and never speak a word. We had signs for everything. This little gem here is a power reverse gear, forward, over here, and back. We don't have air yet, we will see how this works later on. On many older engines, they called it a Johnson bar. And it was a manually operated reverse thing and had a big old reverse lever. Looked something like this, only it was about 4 feet tall, sometimes 5 feet tall. And you had to get up and then wrestle this thing around and probably end up with a double hernia and broken back and a few other things. Later on, the Interstate Commerce Commission said any locomotive weighing over 150,000 pounds on the driving wheels had to be equipped with a power reverse gear. Up here, this handle here goes outside to a throttle valve out there, and this is steam to the cylinder cock. These cylinders are 25 inches in diameter, and the piston has a 30-inch stroke. That's quite a large cylinder. Yet there's very little clearance on the heads. There's probably only perhaps a 1/4 of an inch clearance, and water doesn't compress. So if you get a lot of water in there and the piston comes forward, it can actually blow the head right off the cylinder. That you don't want. Another big, lots of trouble, and the mechanical department just love you for doing things like that. Plus the fact the engine will probably be out of service for several days while they do it. When we get going, why then we turn this and they close. You don't want them open all the time because they waste a lot of steam and you lose power, and it keeps everybody awake.
It's the kind of job that you have to have a disposition for paying attention to what you're doing. You can't really drift too much, particularly like on the spot here you can a little and talk and whatever, but when you're actually out on the road and you're working, you're really managing your steam pressure, you're watching your water, and you're very busy. And there's a lot to do. You're the left eye of the engineer. He can't see much if you're going, or he can't see anything if you're going around a left-hand turn. And if you're going, as far as if you look down the locomotive, you're pretty well blind about 30, 40 yards in. You can't see much in front of the locomotive that close in. So essentially what you're doing is you've got to have an attitude where where you pay attention to what you're doing. You can't kind of drift, because once the steam starts to get away from you, it takes quite a bit to get it back. If the steam starts to drop, you have to start walking your valve one notch here and making various adjustments. A steam locomotive basically they fire the same, but all engines have different characteristics. So in a sense, they fire different. And even though they may be the same class of locomotive, they have different characteristics. So you just have to watch your water when it starts, and you have to manage that water supply. If you're working full throttle, you're carrying about maybe 2/3 to 3/4 of a glass. When the engineer's going to shut off, the water level is going to drop a little bit, and you kind of have to prepare that so when he starts up again, you've got enough water in it and you can keep your steam on the point. When he needs the steam, he needs it when he's working the engine. When he starts out and he works a hard throttle, that's when he wants his 210 pounds. Well, the teamwork it's for some verbal. A lot of it, if we're calling signals, we'll use the air valve, kind of saves the voice a little bit, or we'll call out a green and he'll wave to me in response and vice versa. So we communicate the signals, that's number one, to know the track is clear. My communication with the engineer is I watch him. So as I'm going down the road, I'd be in this position here looking out the window. I'm looking at my steam gauge, I'm looking at my water, and I've got my eye on him and the throttle. Is I'm supplying power for the engineer. He's got to have steam pressure, and I've got to make sure the boiler is safe so she has plenty of water in her. You can't make steam without water, and you don't want to run low water in any of these types of boilers. Well, a clean stack tells me that the fire is burning efficiently. If I wanted to get maximum heat out of the oil I've got in there, then I would be burning a light brown haze. And if you can't do it with a light brown haze, why then you've probably got something wrong, and it's something you have to look into. Either the fire is out of adjustment, or you've got a dirty flue, your boiler's not steaming as well as it should.
The first thing, of course, is that you have to know that it's safe to move the locomotive. Right now, we have our blue flag up here. The engine is not to be moved under any circumstances, not to be coupled onto by another locomotive or cars. And this is a safeguard for people working on and about the locomotive, and it is to be respected at all times. The person putting this flag up is the person that takes it down. And when he takes it down, it's his responsibility to know that it is safe to move the locomotive. You've got to look around, make sure that the chains are out from underneath the locomotive. You have to make sure that the brakes are applied on the locomotive and the tender. As a matter of fact, you do that before you take the chains out, so that the engine does not roll away on you or there's any kind of an uncontrolled movement. After you've walked around and ascertained that it's safe to move, you do that. Fine. To do that, you move the reverse lever all the way into the forward position. You release the locomotive brake and you open the throttle gently. None of this jerking it around. These things do not react like a gasoline engine or an electric motor. You have to give them time. You open this, you could watch your steam chest pressure will gradually start building up. This engine will generally move on about 60 pounds of steam chest pressure. Then, of course, the speed is simply regulated by how much throttle you give it. You move for quite some distance with the cylinder cocks open, allowing the water to work out of the valves of the pistons as they're going back and forth out there.
Basically, what we're doing here, if the engineer was going to move the locomotive light, my major concern would be that the fire stays lit when we're drifting. So I would try to keep the fire bright, and he's not going to work enough throttle where I'm going to have to really make some radical changes, but I may need a notch or two just to keep the fire lit while he's exhausting. I'm going to back up, so we'll ring the bell a little bit.
Here we go, back up.
All right, back up. Now as the engine starts exhausting, I'm just going to try to keep the fire, I'm looking at it through the peephole there, keep it from going out, keep a bright color in it. And at the same time, we'll try to maintain our steam pressure a little bit. And we'll look back out the window here to see where we're going. About 2.5 car lengths, Neil.
Okay.
Now you got about 2.
All right.
You got about 1 now, Neil.
1. Back down and couple onto the train. That time, the carman would couple up the air hose between the tender and the cars and cut in the air. The brake pipe pressure would drop, pump would go to work, and you sit here and pump on them until in freight 90 pounds, passenger 110, get the desired pressure up, the brakes are charged. Well, I guess we're all ready to start ahead, so first thing we'll do is see if we can get a sign from our brakeman on the rear end. Okay, so it's all right to go, so put the engine into forward motion. We'll release the engine brake and open the throttle, and hopefully, here in a minute, we'll go.
Headlight, little bell. Now throttle's open. We'll walk the firing valve here a couple of notches to keep it in there. If I hear the engine start to slip, and I'm going to give it enough oil to the fire so he doesn't draw my fire out and put the fire out. If the engine kind of recovers and starts to grip the tracks again, he's going to widen out on it again, then I will graduate my firing valve. Now, assuming now the engine's not going to slip anymore and you're starting to take the load, we know, you can tell, a couple of good exhausts and you know when you have it, you got that feel for it. What I'm going to do is that the engine starts to chug maybe 3, 4, 5 times. I'm going to walk the valve up and keep that pressure right at 210. But I'm going to have about 5 or 6 notches here that I can play with the oil valve before I have a maximum fire. And in order for me to determine that, I have to look out the stack or look through this window at the stack. When I see a light brown haze coming out of the stack, then I know I've achieved my own personal maximum fire.
Once we get out, we get the train moving. Well, we get out on the main line and we chug along. Yard tracks out of yards and things, 5, 10 miles an hour, depending on the railroad and whatever. We get out on the main line, we're going to go, let's say 60-mile-an-hour speed limit, you would just gradually move the throttle on out until you're all the way out here with it. By this time, we'd probably have 190 pounds. Normally on a road running along at good speed, the back pressure should be around 5, 6 pounds. As the speed starts increasing, you start notching up. As you notice, the quadrant here has 50, 60 teeth on it here. What you're doing is shortening the valve travel out there, which means the valve cuts the steam off to the cylinder at an earlier time. With the reverse lever all the way down, this engine is probably getting steam in the cylinder for about 70% of the stroke. For 21 inches, at which time the valve would cut the steam off. At very high speeds with this engine, you're probably admitting steam only to about 10% of the stroke. You're probably only admitting steam for about the first 3 or 4 inches of the stroke. The rest of it is all done by expansion. That's one of the most wonderful things that the steam engine had going for itself, was the expansive power of the steam. The proper handling of the reverse lever is very, very important. It's really best and the most efficient if you can operate the locomotive with the throttle wide open, because the steam at very high pressure in here has more expansive power and therefore is more efficient. On a long run passenger train like the Daylight or the Lark, you're going along 70 miles an hour and you want to stop at, we'll say, Salina. The first thing you would do is probably make a reduction here. Now this is going to make a little bit of noise, so hold on. Now you reduce the brake pipe by 10 pounds. Back on the cars, you get 2.5 times the 10, which means in the brake cylinders on the coaches and the sleeping cars back there now, you have 25 pounds per square inch in the brake cylinders back there. That'll do quite a little bit of work. Now, we always kept the engine brake released. As you can see here, the engine brake has come on now to 25 pounds, and that you don't want. So, this has a return spring in here, and you go over against that. You have to hold it there. The pressure will drop. Well, now the engine brake is released, but you still got the train brake on. And now, okay, at this time, now you would start to gradually close the throttle. You'd get it down a ways, and it would be good to drop the reverse lever down some. then you know you've got to kind of play it by ear. It's like making a three-point landing. You have to feel your way in. You have to have a feeling, hey, is the thing slowing down fast enough? Are we going to get stopped at the depot? Or are we going to go by? If we're going to go by, hey, fine, we're going to have to make another reduction and put the brakes on harder back on the cars. Now we have a 20-pound reduction. You have about 50 pounds of brake cylinder pressure in the coaches, which is probably as high as you'd want to go. And so you keep throttling down and you keep dropping the reverse lever down. The idea is when you come into the station, you just barely got the throttle open. This may be showing 15, 20 pounds steam chest pressure. Engine brake release like this. And then when you get down to your spot, now if you've got to take water, you had to be very careful. Because if you got by the water spot, the only thing you could do was back up. That's kind of hard to do because when you stop with a passenger train, people are getting on and off and one thing or another, so you just can't back up. So the best thing to do is come in very cautiously on a passenger train, especially if you had to take water. And be sure and hit the spot. This tank does have 3 manholes up there on it, so you have about 15-foot leeway there. But you're gonna have to stop within about a 15-foot stretch. We had marks on the ground. We called them water marks, and you wanted those right underneath the cab window. And if you did that, that meant you were properly spotted for water, so the fireman could go up and take water. The idea is when you come to a stop on passenger cars, the brakes can be graduated off. And the idea is, like your automobile, you come up to a stoplight, you're going 50 miles an hour, you have to press down fairly hard on the brake pedal of your car. As the speed gets down and you come up to the light, whether you realize it or not, you're letting pressure off of the brake pedal so you don't throw yourself through the windshield when you stop. Passenger train, you have to remember there are people back there walking around, eating dinner in the diner, or if they're lucky, having a highball in the lounge car. And so you have to take that, or at night, people are sleeping. You don't want to wake them up. So we would come in then, and as the speed decreases on anything, the braking force increases. So what we would do is you'd come in like this, and you see it come back up a little bit. Well, what you're doing back there is the graduating valves on the cars will allow some of the brake cylinder pressure to escape to the atmosphere, thereby cutting down pressure in the brake cylinder. The ideal thing to do was to come to a stop with the throttle shut off, reverse lever in the corner, and just as you come to a stop, you'd release it like that, and of course the brakes don't let go that fast. They release through a retaining valve which has a choke in it, and it would take the brakes maybe 15 or 20 seconds to completely release on the car. The ideal way, and what everyone strived for, was to come to a stop, the throttle shut off, reverse lever down here, and the last whisper of air coming out of the retaining valves on the cars to make a nice smooth stop.
Okay, now as you're rolling into the depot, you got to remember I have no blower on. I have a full turn atomizer in this engine, 3/4 full turn, good bright fire. I have a water pump that's working, and I've kind of graduated my water up a little bit. Now, when the engineer goes to the automatic train brake, I hear it. So I know that he's going to make some adjustments over there to plan his stop. Well, I've got a plan for him. So now the first thing I do is I'll turn first of all, I'm going to turn the blower on where I normally would turn it, in this case about a half a turn, because that would keep a pretty good fire in like what I have here. I'm going to come back on my atomizer about 1/4 turn, and I'm going to shut my pump off. Now I've already added enough water, and if I haven't, then I need more water. I'll go to the injector to do that so I don't chill the boiler. So I'll shut the pump off, have the blower on, have this on. Now I'm ready for him to shut the throttle when he wants to. I'm graduating down on steam pressure, maybe 5 or 6 pounds, depending how long we're going to stay there. And as he's working his way into the depot, he's going to start easing down. As he eases down, I'm already prepared here. I've got a draft going through the firebox. Anyway, I don't need his exhaust for the draft. So I will just walk my valve down to where I have it set on the firing pin as he shuts off. It makes a nice smooth transition. Normally, my steam pressure, if it's back about 5 or 6 pounds, it'll start climbing once I get into the depot. If I've done it right, the water will drop to the level I want it at when we start. As we stop into the depot, we're there 3 or 4 minutes, the steam pressure will continue to work up, and when he gets the high ball to move out again, I've got my 210 pounds, I've got my water where I want it, and I simply reverse the procedure that I indicated before, shutting off as he opens the throttle up. So you're kind of planning this stop to stop.
I always like about 100 feet before I was going to come to a stop, I would put the sanders on. That way when you stop, the locomotive was sitting on sand. Now when you get ready to leave, put that down and you could go right at them. Put the sand on and the engine won't slip because it's already sitting on sand. If you come in and stop and then try to leave and the engine wants to slip, well, it has to move about 30 feet before you get all of the wheels on the sand. So if you put the sand on maybe a car length or so before you stop, when you stop, the engine's already sitting on sand. Now you're ready to go without slipping the wheels.
This particular series of 484 locomotives were designed as a cooperative effort by the American Locomotive Company and Union Pacific. They've never really been accorded the recognition that they should have had. They're very high capacity locomotives, high capacity both in terms of the amount of steam they can produce and the amount of work that they can produce. It's a very well-rounded design. It's a very modern design. It kind of represents the state of the art as the art existed in the late 30s and the early 40s, because research work on steam locomotives virtually came to an end about then.
Well, the fireman's duties are not only sitting in the chair. When I come down to work in the morning, I have to relieve the night crew. I also have to make sure that the tender is full of water, the tender is full of oil. If not, why? I've also got to get drinking water and ice since we have no refrigerator. I have to go turn on the air pump so we have air to move. I pull the chains, pull the blue flags if we're done working, make up the air hoses, make sure we got air going through what we're going out to the train with. I probably forgot something, but I usually do every morning. I forget something. I've got valves to close on the outside, and the mechanical department has a certain number of things they do also. I'm supposed to check to make sure to see that that's done. And the boss, old Steve, shows up. He'll go around and check, make sure that I checked up on them and everything is all ready to go. It's not a come down, kick the tire, climb on and go. It's quite a bit of preparation before we get on and go.
Now, it does not have roller bearing rods. They tried them on 2 different locomotives and they were more trouble than they were worth. So when these locomotives were ordered, they did not go to roller bearing rods. They stayed with the old bronze bushing, which is inside the rod on each pin. That's grease lubricated, and it has to be lubricated. Practice back in the old days and now was you'd run not more than 150 miles without renewing the grease in those bushings. Another point of a modern locomotive is mechanical lubrication. Now, I mentioned the rod bearings. Those are the only things that have to be lubricated manually. All of the axles on the locomotive are roller bearing equipped, and the only maintenance they require is to check the oil about once a month. That's all you have to do to them. But there are hundreds of moving parts and moving points on the locomotive. Older type locomotives either used hand lubrication, as the old long spout engineer's oil cans, or they used a hydrostatic lubricator, which was a lubricator that used steam and oil. It mixed the steam with the oil, and it used the steam pressure to
to take the oil to the various lube points. That was obsolete in the 20s. These locomotives are equipped with mechanical lubricators, which are actuated off the valve gear. That thing holds 2.5 gallons of oil, and you can see the many lines coming off of it, the many pipes coming off of it. The feed water heater consists of 3 parts. You start out with the cold water pump. That's a steam-driven turbine pump that takes water right out of the tender, right through this hose, and the water in the tender is at whatever temperature, ambient temperature. Cold water pump pumps the water up into a box up in the top of the smoke box, right ahead of the exhaust stack. And there, of course, inside that stack, the temperatures vary from 12 to 1800 degrees. There's a box inside there with a cooling coil, with a coil in it. The cold water goes through the coil. The coil is surrounded by the exhaust steam. The exhaust steam heats the water. It heats it to almost 300 degrees, already past the boiling point. From that point, the preheated water goes to the hot water pump. And the hot water pump is right here. This is a piston type pump, and it takes the preheated water out of the smoke box and pumps it into the boiler. The reason it's a piston type pump is it has to ram that water in against the 300 pounds boiler pressure that's trying to come back out through the pipe. You turn the whole works on with a little valve in the cab that starts the steam turbine pump, and it starts the water pump pumping back and forth, pumping the water in. Okay, we'll put her in gear. Keep the brakes off and go. Most railroads back in steam days didn't trust the builders to do their own design work. Each railroad had its own engineering staff, its own huge design staff, and each railroad felt that it had to have custom-built power. If the Union Pacific designed an extraordinary locomotive, the rest of the railroads would say, well, that's fine for the UP, but we've got to have our own. UP work was very close to American Locomotive Company. The largest, most modern locomotives on the UP were built as a cooperative effort with ALCO. Their design staff and the railroad's design staff worked very closely together. And there were some disagreements, and there were some fine arguments if you read the minutes of some of the meetings. The UP developed the first high-speed 484s. We did not develop the 484 type, but we did develop it into a high-speed locomotive. The railroad was looking for passenger locomotives that could run 90 miles an hour on flat track with 26 cars. And the UP produced a design, the builder produced a design. The two designs were very far apart. There were a number of things that the UP had tried that the builder said was impossible. So there was quite a bit of give and take. And finally they said, look, it's our money, build a locomotive the way we said. If it doesn't work, then it's our problem. They built it. It exceeded everybody's expectations, and it proved to the industry that a big locomotive that could pull both freight and passenger economically could be built. The locomotive has a one-piece cast steel frame. That means the entire frame from the pilot all the way back to under the cab was one giant sand casting, one-piece cast steel. On older locomotives, more primitive locomotives, the frame was built up of hundreds of individual pieces. The bolts would work loose, they would break over time, the frame would bend, the wheels would get out of alignment and all that. That's not a problem with a cast steel underframe. It makes a very solid foundation. The drivers are a one-piece cast steel box casting. This is much preferred to the old obsolete spoke type drivers. For one thing, it's much stronger. For another, it's easier to balance, and that's very important in a high-speed locomotive such as the 844. The rods are made of a very high-strength alloy. It's a manganese vanadium alloy. You'll notice they're not very big. They have a very, very high section modulus with very high strength. Rod failures were virtually unknown with these locomotives. Okay, you can divide the cab of a locomotive down the middle. Everything on the right belongs to the engineer, everything on the left belongs to the fireman. Then you can further subdivide that almost horizontally. You have the valves up along the roof line. These are valves that you will either turn on or turn off when you fire the locomotive up or prepare it for service. And you don't ever fool with them again until the end of the run or you're ready to shut the locomotive down. Right now they're all on. There's a water glass on this side, a water glass on that side. That's so both of us can keep an eye on the level of the water in the boiler. And there's a valve to shut off the water glass at the top and the bottom. That's for just in case the glass should break. Of course, if it does, the cab is full of hot water and live steam, so you've got to be able to shut it off. You don't want to stay in here with the hot water and live steam, so you see an extension rod that runs right through the back wall. That glass breaks, you dive out the back door and shut the valve off from back there. On the right side water glass, that's connected to a water column. It has 3 tricocks. That's to make sure the glass isn't lying to you. You have to know what the water level is. And if it gets sediment or something in it to block it up, it may be lying to you. You may think you have water and you don't. So you double check it with these tricocks. You open them up, and if water comes out, you know you've got water to that height. You open the next higher one until you find out where the water ends and the steam begins. And you do that like this. You see the water come out, you know you've got water. You get down into the operating controls, everything that I'm going to have to use or everything that Lynn's going to have to use on his side that we're going to have to use regularly is here close at hand, where we don't have to be jumping around to get a hold of it. We've got the throttle, the air brake gauges, back pressure gauge that I have to look at, the cab signals, the train brake, the engine brake, cylinder cock valves. The little brass handle here controls the sanders. They're off right now. You push it forward, that turns them on. The sand blows down in front of the wheels for traction. This is the bell valve, reverse gear, all the way forward, all the way to reverse. It's in neutral right now. You can see all the little notches. Those are the different adjustments in the valve gear. As the locomotive goes down the railroad, the speed increases. We'll hook it back. As the speed decreases or the amount of work required increases, we'll hook it forward. This is an air-operated blowdown valve. The cab signal acknowledger, when the cab signal indication changes, a warning whistle sounds in the cab, and you acknowledge it by doing that. The only other gauges I have to concern myself with is the boiler pressure gauge and the speedometer. And the rest of it is looking out the window, listening to the stack, and feeling the locomotive through the seat of your pants and figuring out what the train's doing and what you're doing and how to handle it. The only other device over here that I haven't pointed out that's very important is this, and that's the whistle.
Okay, basically my job as a fireman is to make a fire, and that's where the action takes place. My side of the cab to make the fire has 3 controls that I generally use all the time and pretty much continuously. I've got my oil feed valve here. Oil flows from the tender down underneath the locomotive by gravity. This valve goes through the floor and controls the amount running down out of that particular pipe. I have got an atomizer here, which is nothing but steam pressure that blows the oil out into the firebox. You can hear it. The more steam I use to blow it out, I can actually blow the fire and put it out if I do it wrong. All right, but my atomizer basically helps the oil to burn. Just running in there, it would not burn. You can't get enough oil moving, and it's basically in too large of chunks. So what you do, use the steam, it breaks it up into tiny mist and burns. In combination with this and the amount of draw that the locomotive is, judging by how much throttle is on there, several different factors, is how you tune it. Basically, my job is to tune it as we're driving along down the road. The blower that you see right here is what we're using to create an artificial draft while we're sitting here and the throttle is not open. Main thing I'm worried about over here is water. This is my feed water pump. I have a water glass on this side. I worry more about this than the pressure. This is the boiler pressure. He's got one over there. If it falls too low, I get yelled at. If this falls too low, go below this line. The crown sheet has been known to get hot. It will rupture. That's called a boiler explosion. Nobody survives those. We do not want that to happen. This particular feed water pump is very easy to operate. Steve showed you the turbine for the pump and the little ram engine up underneath here, and you can hear it. That's how easy it is to put water in on this one with a feed water pump. When you're going down the road, if you're working a heavier train than what we had today, you kind of figure I've got a little notch here. You set it to where it's using the same amount of water that you're putting in. Then you can adjust this, adjust your smoke so you got a nice light gray stack, and everything will stay absolutely even, theoretically, forever. But then of course you always got a hill, you've got a town that says slow down to 45. He puts in the throttle, I've got to rearrange these three. He comes out on the throttle, I got to rearrange these three again. I have a cab signal device on my side that's a repeat of the other side, so I don't have to get up and go over and see if he's obeying the rules, because this is co-responsibility. At home, you've got to draft your fireplace. It's a big, heavy one. It's about this big by this big, and it's made of iron. That controls the amount of air going into the firebox. Fire in this particular engine with that particular man over there running is kind of like driving a stick shift car. Once you get used to it, it becomes second nature because he is very good at what he does. It makes my job so much easier. If he were to get mad at me, he could really make it rough on me. But what he'll do, when he toot, I know we're going to go, he releases the brakes, he drags out the throttle over there. Well, I've got to be ready.
Assuming everything else is done, you're coupled to a train, the air test is complete, and you've got a signal to leave and all that sort of thing. First thing you'll do is stand up, take the pin out, and put it back over here so it doesn't flap around and break the glass out of the gauges. We'll shove the reverse gear forward, crack the throttle by pulling it back a small amount, and release the engine brake. Make sure the cylinder cocks are open. The locomotive doesn't move within a reasonable amount of time, we'll give it more throttle, a little more throttle, a little more throttle until it either starts to move or the wheels slip, one or the other. Once it starts to move, we'll shut it back off and work it slowly until we stretch all the slack out in the train. If you leave it open and you start jerking the cars, why, the further back, the greater impact there is in the train. Pretty soon you're knocking people on their cans back there. Starting the train is a pretty tricky process to do it right. Once you've got it moving, then you'll close the cylinder cocks, and you'll have more power that way. The only reason you have the cylinder cocks open is to blow out all the condensation. The locomotive's been setting for a long time. There'll be a couple dozen gallons of water in the cylinders and superheaters and everything else. And you've got to get all of that out of there. If not, you can blow a cylinder head, or a lot of other things can happen. All of them are bad.
As the engine starts going and she starts talking to me, I'll start feeding her a little more oil. I've got to give it a little more atomizer because I'm breaking up more oil to burn. Watching my smokestack to make sure I don't have too much smoke. Now, all the water in the boiler is going to come back this way. So it will show glass will be full where the front won't be full, so I've got to keep that in mind. Also going down hills, it all runs to the front end and it shows there's hardly any here when you really do have some. That's something else you have to keep track of. But as our speed increases, I will continue giving you more oil for more power. The closer I am to 300 pounds, then we're up to about, say approximately 4,000 to 5,000 horsepower on a good day.
Well, what you're trying to do is get the locomotive where it'll maintain the speed that you want with the minimum amount of steam and consequently the minimum amount of water and fuel being used, and you do that by making minute adjustments on the reverse gear and the throttle until you get everything like you want it. Small changes in the gradient, either up or down, or from one of those conditions to level or vice versa, will change everything that's going on here, and you have to change accordingly. So you'll see making different adjustments in the reverse gear. I'll shove it forward. If I want to accelerate a little bit, I'll shove it forward a few notches. When it's starting to pick up like I want it to, I'll start bringing it back a few notches. Municipal speed restrictions, like there's a 45-mile-an-hour speed limit through Central City. And we're sailing along at 65, and I just set the brakes enough to bring us down to 45, kick them off, and I didn't touch the throttle or the reverser. As soon as I kick the brakes off, the engine will start to pick it back up.
One of the reasons this is a rougher riding engine, maybe because we have 450 tons going down the road, and it's checking every joint and every low spot and every little soft spot on the railroad. Seeing us from the roadside, it looks like it's a smooth ride, but it's not. You see it going down the railroad. If we're going slow enough, you can actually see the ties and the rail flexing. Now, you hit a bridge, and you can tell immediately up here. When we got on that bridge there at Columbus, everything is rock solid, nothing moved. Got off the other end and it went like this because the ground is softer and compressible. The bridge doesn't compress. That oil and stuff going through condensing on my fluids. It'll form a layer on there. That layer is like insulation. If you got a big train, you need maximum horsepower. So what I have to do is sand the fluids. We have scoop. Another one. Plain old children's sand. When it's working hard, there is a real draft going in there, and I'll pour about 3 scoops of this in. What that'll do is it's flying down, bouncing around inside those holes and flues. It knocks all that soot loose. That's where you get that black cloud. Now that's going to come down somewhere. But I have to do it about 2 or 3 times to get all that out of there so I can get maximum horsepower.
There's always things to fool with. Of course, when the cap signals change, as they did a number of times, they have to be acknowledged. You're talking on the radio, you're thinking 3 or 4 miles down the road where you're going to have to slow down or where you're going to have to stop.
And we knew exactly where it was they wanted to go, and nobody knew how to get there except for a roundabout way.
Then you're thinking, where am I going to apply the brake? How much am I going to apply? How long am I going to leave it applied? What am I going to do with the throttle and the reverse? Exactly where do I want to stop and how do I want to stop? Are trains coming? Or the dispatcher trying to call me? Where's the slack in my train? What's the speed limit here? What's the speed limit down the road? That's just part of it. Also watching the water, watching the steam pressure, watching the smoke. And before I'm doing anything drastic over here, I have to make sure that he's either watching or listening, because whatever I do over here, he has to make adjustments to compensate.
When he comes into a town or when he shuts the throttle off, he'll generally glance over at me. I know he's going to do something. I usually start coming back less oil into the engine, because when he throws that throttle in, all of a sudden we don't have any draft and you get this big blah of black garbage up in the sky. Now a lot of the rail fans love to see it, but the housewives with their laundry out or the Greenpeace people do not like to see that sort of thing, and it is air pollution. So we keep it down to an absolute minimum at all times.
Locomotive operates on 300 pounds boiler pressure. It's rated at 63,000 pounds plus tractive effort, which is probably a conservative rating. They were tested out at over 5,000 cylinder horsepower, which again is a conservative rating. We know that the locomotive can outdo that. There are test reports and test results that indicate it can perform far beyond what the design engineers calculated that it could do. It has very high superheating capability. By that, it produces 750 degrees steam, which is very hot, very dry steam, which produces the most work. It has a feed water heater, which preheats the water before it goes into the boiler. It uses the exhaust steam to do that, which saves a lot of fuel. It has roller bearings. It has 80-inch drivers. It has one-piece cast steel frame. And it has many other small features that can't be seen because they're inside or underneath. But they were very well-liked locomotives. They were very efficient locomotives. Even though they were designed for passenger service, they were very successful in freight service after passenger trains were dieselized. And they found that the maintenance costs were much less than they had anticipated. The availability was much higher than anticipated. Locomotives could pull heavier trains than it was thought that they could pull. The tonnage ratings on them were increased several times over the lives of the locomotive, and they can still pull more than their rated tonnage. It's just a good all-around locomotive.
The way you get to learn all this stuff, I'm a railroader by trade, been doing it since 1968, been working for the railroad, been working on the steam engine now since started in 79, helped a group of employees restore a Union Pacific Challenger 3985 in Cheyenne. I'd never seen a steam engine that big running before, so I wanted to help get it running. Well, we still had old timers around here then that actually ran these things when they were new. And they knew the ropes, and those of us that showed any interest whatsoever, they took the time to explain to us and tell us and actually gave us experience down here firing it. And that's basically how I learned. Experience. Just plain old experience.
I've been an engineer for 20 years, and it's just by experience and by doing. That's all. In the old days, you had to go through a series of progressive exams taken over 3 years to be promoted from fireman to engineer. It's not quite that stringent nowadays, but there are still very specific tests that have to be done. But even the test, once you pass the test, you still got to become seasoned, and the only way you become seasoned is by working all kinds of trains, all kinds of hours, all kinds of weather conditions. No two trips are the same, no two trains are the same, and it just takes years of doing.
New from Phoenix Media, Grandpa Worked on the Railroad, a musical train school for young engineers.
D, expands, the piston goes back, it pushes on the rock to move the wheels on the track. Now the firemen shovel the coal in the fire.
Go slow, drop your arms and stop, and slow things in like that.
All right, away you go. Now, if we just use our imagination.
Whoa!
Engines are big and full of steam to run.